I'm Garrett Caproot. This is Evan Dusky, Nick Matrulli, and Hudson Hector, and we are the stainless steel hardness testers. We tested 17.7 pH stainless steel at different locations, and comparing these to industry standards of C38 the Rockwell hardness test. The key question we were asked is it possible to treat 17.7 pH stainless steel in-house, achieving results at industry standard? Of our background, heat treat oven owned by Speed Teams, prior work done on 4340 treating in-house, results gained through 17.7 pH experiment would yield results from many different school teams in their own manufacturing. Our new approach was the 17.7 pH was unfamiliar to us in this setting, as any major heat treat work previously has been shipped out to commercial resources. Our approach reduced overhead costs and lead time. Why this matters: Speed Teams at Clarkson can work to incorporate more 17.7 pH into their design, as the work previously done off-site can now be done in-house. This reduces team budgets and downtime. The engineering models and relevant theoretical heat treating industry standard TH 1050 served as a baseline for our project testing parameters. The results yielded hardness values lower than we expected, but does display the expected result trends.
In terms of our methods for this experiment, seen through both the table and the experimental flow chart on this slide, first step is preheat the oven to a specified temperature. After that reaches that point, I add the 17.7 to the oven and then soak the samples in the oven for a specified testing time based on research we did. After it's in there for that time, remove it from the oven and transfer to a quenching medium. For this experiment, we determined air to be the best medium for that and let it sit out there for about an hour or so. Once that time passes, place the samples back in the oven at a lower temperature for a different specified time. Once they reach that, again, we're going to remove them and let them cool to room temperature for the final time. After they're cooled off, descale them and bring them over to our indenter and actually measure the hardness of each sample. Repeat steps 1 through 8 and vary our soak times of the samples in the oven to see if we can either get harder samples, less hard samples, and see if there's an optimal recipe. We started right in the middle at 90 minutes for an initial soak and 90 minutes for a secondary soak, and then deviated 30 minutes both upward and downward from that, giving us 9 total samples. Moving on with further methods in terms of relevant variables, time of primary and secondary soak were our main factors we were changing in this experiment, and our controls stayed the same. Those are going to be the 2 temperatures in the oven, 1400 degrees Fahrenheit for an initial soaking temperature, and then 1050 degrees Fahrenheit for our secondary soak temperature. For measurement, we use a variety of different instruments to gain data for this experiment. The heat treat oven itself has an LCD readout on it, both for live temperature and preset temperature. We used an infrared thermometer to quick laser the samples to make sure they were safe for handling and to ensure that they were cooled down furthest to the temperature we need them to, roughly 55 degrees. And then we also used the indenter, which had a dial indicator on it to actually indicate the hardness that the material was achieved. In terms of test equipment, Hotshot 1200 heat treat oven is the oven that we have. There was the Rockwell hardness tester, which was supplied through both the machine shop and Professor Hoover. 9 17.7 pH stainless steel samples at 1/8 inch thick. Welding gloves, face shield, and tongs. Mainly just PPE stuff for handling both the hot and sharp samples. Schedule: all of our constraints set at both the beginning of the experiment and laid out through the 401 curriculum were met without issue. And in terms of a budget, all of our key components in this experiment we already had on campus, but if they had to be purchased separately, price would exceed around $1,800. The oven being a big chunk of that at around $1,400 or $1,500 by itself. And then also on the right-hand side of this slide is a quick risk analysis, recognize hazards, assess risks, minimize, and prepare.
As shown in the table here, an initial soak of 90 minutes at 1400 degrees Fahrenheit with a secondary soak of 90 minutes at 1050 degrees Fahrenheit yielded the best results. This is in line with industry standard. However, we did not quite hit the industry standard hardness of C38 Rockwell hardness. This could be due to a variety of different factors, such as not scuffing the test sample enough when we were testing, or anything in between, such as leaving it out too long at didn't quite get to 55 degrees. Could be anything like that. The graphs shown here help paint a better picture of the results. As shown with the 60 minutes initial soak at 1400 degrees, it doesn't give quite enough time for internal stresses to be built up in the sample, yielding a lower hardness all around. The 90-minute initial soak gives the just right amount of time for the internal stresses, and with the 90-minute secondary soak, it gives enough time to anneal those internal stresses to the right point too, to give the best hardness. 120-minute initial soak at 1400 degrees is too long. The initial stresses are formed and then relieved later in the secondary soak, causing it to be not as hard but more tough.
After performing the experiment, it was safe to assume that we achieved our goal of plus or minus 3 Rockwell hardness. This goal was set to be close to the industry standards of our material. We ended up getting average around like 35, C35 for hardness, when industry standards about C38. The error of -3 could be a result of us using a wire brush. When we were testing it, some of the scale was still left on the material. To change this, maybe next time we can use like a wire brush, or maybe wet sand the rotors on a piece of granite. Another source of error could have been our control time when we were soaking the samples outside. Given how long the experiment was, it was very difficult to try and control the air temperature, because we do this during different times of the day. So maybe next time when we do this, we can perform these all at one time during the night. Next steps, we are going to try to explore different thicknesses of the same material for our use of Baja brake rotors. To continue our research, we have to research different types of material that we could be using.